Hello, everyone. Thank you very much for joining this session today. My name is Dr. Weston Umstead. I am the Senior Product Manager for DeSales Chiral Technologies. My degree is originally in organic chemistry, and after graduating in 2016, I found myself working at DeSales Chiral Technologies in analytical chemistry. So I've been with the company for going on 9 years now. I do everything from chiral method development to product development, application development, technical support, troubleshooting, sort of a jack of all trades. But the focus of our talk today, as my cover slide has here, is on the use of polysaccharide-based chiral stationary phases for the achiral and chiral separation of cannabinoids. Some of those terms might not be familiar to you right now, but hopefully by the end of this presentation, everything that I just said there will make complete sense, and we'll have a good idea as to why we're using these phases for these types of separations, and some of the new work and applications that are being done using those. So just kind of covering the topics of interest today, I think the area that most of us are probably not very familiar with is going to be the chiral chromatography piece. And so I'm going to spend a little bit of time to kind of go over the background of chiral chromatography, where it's historically been used, and why it has some really powerful applications in the cannabis field. Post 2018, kind of where the focus was, and achiral separations for cannabinoids. What exactly does that mean? What were the technologies that were being used? And then more recently, where has the emphasis kind of shifted a little bit more into the actual chiral separation of cannabinoids? Why is that important, and kind of where those new applications are being developed right now? So starting first, this background section on chiral chromatography. Why is chirality important? If you're a fan of Billy Joel or a fan of history, there's a good chance that you've heard of thalidomide at some point in time. In the late 1950s, early 1960s, thalidomide was a drug that was prescribed to pregnant mothers, specifically in Europe, for the treatment of morning sickness. Now, as it turns out, thalidomide is actually a pair of what we call enantiomers. Enantiomers are non-superimposable mirror images of each other. So we oftentimes view them as they're obviously images of each other, not superimposable. And the is that oftentimes one has a certain effect on the body, the other has a different effect. And so in the case of thalidomide, it was the R enantiomer that was providing the benefit for morning sickness. And the S enantiomer that was also present was actually a teratogen, and it was causing some pretty significant birth defects for the children that were being born, missing or deformed limbs primarily. So there was this discussion around what can we do about this? How do we solve this problem? It took a little bit of time to come up with the solution. But even before thalidomide, there were a number of early accounts on chemical differences from chirality. You might know that Louis Pasteur famously was able to separate the crystals of tartaric acid, D and L tartaric acid, because he noticed that the two structures gave two different crystal forms. And so he was, under a microscope, visually able to see the difference and separate those crystals. A French physicist, Biot, noticed that there were two different forms of quartz, and that they reflected light differently. And so there were some activity differences because of the structure of these compounds and them being different. But fast forwarding to the solution was basically, we need to come up with a technology that's able to discriminate between these two enantiomers, and then do an assessment of them before the drug's actually commercialized or studied. Why is that important? Well, historically, and even to this day, it's estimated that around 80% of all of these small molecule drugs that are in development contain one chiral center. So almost all of the drugs that are being studied need a chiral analysis done on them in order to make sure that we don't have another case of thalidomide. Now, those chiral centers can be a little bit different depending upon the drug compound. Most often when we're talking about chiral centers, we're talking about carbon, but nitrogen, sulfur, and phosphorus are also capable of forming what we call a tetrahedral chiral center, or an sp3 carbon center. Basically, imagine an atom, carbon, nitrogen, sulfur, or phosphorus, that has 4 different things attached to it. And if you have that, then geometrically, those 4 things can be oriented around that chiral center differently, in such that they are mirror images of each other that are non-superimposable, and again, interact with the body differently. NSAIDs, beta blockers, antidepressants, and a lot more other types of drug compounds contain these chiral centers. I have a few examples on the screen here. On the left-hand side, you've got a chiral center located approximately 2 o'clock in the molecule. You'll see there's an OH group that's attached to a carbon that then has 4 different things attached to it. The one in the center, the chiral center, is going to be directly right in the center of the compound, right below the 5-membered ring with the oxygen in it. You've got a carbon there that's got 4 different things attached to it. So we need to figure out, how do we separate these things? Well, the solution, or one of the solutions, is chiral stationary phases. There are a lot of different classes of chiral stationary phases. There are chirobiotics, based on naturally occurring compounds in nature. It could be teicoplanin, it could be erythromycin, things like that. There are brush-like compounds, alco as an example. There are other small molecule type selectors. The one that we're going to focus on today, though, are these polysaccharide-based stationary phases. And when I say polysaccharide, I'm talking about either cellulose or amylose, primarily, is what we're going to be dealing with. I have an example on the screen here of what one of those looks like. We've got a cellulosic core that is derivatized with a small molecule selector. In this case, you've got 3 or tris phenylcarbamate. This is handed here is actually the start of where the chiral separations mechanism begins. The handedness of the polymer allows for a discrimination of these 2 enantiomers that we're ultimately going to try to separate. But in forming this helical structure, you have around the outside edge of the core these pockets that we call chiral grooves. And in these chiral grooves, there is a pretty well-established set of intermolecular interactions that can take place. You've got things like hydrogen bonding, pi-pi stacking, steric hindrance, and dipole-dipole interactions that can take place. While we know what those interactions are, it's incredibly complicated to try to predict them, which makes discovering or eliciting chiral separations still to this day a little bit of a challenge. What we know for sure, or at least in terms of an easy way to explain this separations mechanism, is that we want 3 points of interaction to take place between the chiral analytes and the chiral stationary phase. So this picture I have on the right-hand side is demonstrating that. You've got a pair of enantiomers, left hand to right hand, that have all of the same functional groups, but they are geometrically oriented different around that chiral center. So on the left-hand side, you've got 3 points of interaction lining up nicely with 3 points on the chiral stationary phase. And because of that alignment and the energy of binding that takes place, this would be a more retained or later eluding enantiomer. And then on the right-hand side, or sort of in the center of that diagram, you have the opposite enantiomer, same functionality, but because it's oriented geometrically different, there is a mismatch of the binding of those interactions with the chiral stationary phase. So the energy difference being enough allows us to see or elicit a chiral separation. The less energy of binding means less retention, and then therefore it's an earlier eluting compound. And of course, if we take that one and rotate it, we still have a mismatch, and we would still see a chiral separation taking place. Now, I did say that we have two polymers primarily available to us. We have cellulose, which is a glucose polymer constructed primarily of beta linkages. So the beta linkages result in more of a flat, sort of linear organized structure for cellulose. Then in the case of amylose, we have alpha linkages, and that generally gives us a more disordered, a kind of random structure, branched structure. And if we go back and look at examples of what that could be in terms of our chiral polymers, the example on the left-hand side I showed you previously, that's a cellulose tris tris methyl phenylcarbamate, chiral cell OC. And then the amylosic version on the right-hand side visually is very different looking from the cellulosic version. It still has those pockets around the outside edge that we call chiral grooves, but they are more disordered, not as well defined. And so, not knowing anything about chiral chromatography, just looking at these, you'd probably assume that these would behave differently when trying to do a chiral separation. And in fact, if we look at some examples of that, it's absolutely the case. So separation here of prilocaine under normal phase conditions. And when I say normal phase, I'm talking about hexane with an alcohol normally. So here we have hexane isopropanol with diethylamine, DEA. This is a basic compound, so we want to make sure we have a basic additive there to keep everything neutral. If we were to try to separate this on Chiral Pack IA, which is amylosic 3,5-dimethylphenylcarbamate, we see that there's basically no interaction at all that's taking place between the chiral stationary phase and the chiral analyte. There's just a very small hint of a separation. If we change the polymer from amylose to cellulose, but we keep the chiral stationary phase or the chiral selector the same, that would be Chiral Pack IB. We have 3,5-dimethylphenylcarbamate on cellulose, and now we have almost a baseline resolution. We haven't changed the chiral selector at all. All we've done is change the polymer, and we now see almost baseline separation. Now we take it a step further and continue tweaking this chiral stationary phase mechanism, separations mechanism. We keep cellulose, but we change the chiral selector now from 3,5-dimethyl to 3,5-dichloro, which is Chiral Pack IC, and now we have almost too good of a separation. We have a very, very nice baseline separation, very, very strong retention. And so the point of this, when we start talking about developing chiral methods, is that even someone like myself, who's been doing this for almost 9-10 years now, it's challenging to predict what chiral stationary phase you should use with some new chiral analyte. And so we're oftentimes recommending a sort of a screening, a method development screening to get started. You might be thinking to yourself, well, AI is catching on quite strongly here in the last few years. AI should be able to help predict this. But in fact, AI also struggles with this, because when we look at trying to develop models and snapshots of this chiral separations mechanism, we often run into the same problems that, let's say, protein crystallography runs into. You're getting a snapshot of a particular moment in time, the chiral interactions, the structure of the polymer, the strength and the frequency of these intermolecular interactions change as you change other parameters of the separation. So if we change mobile phase, we might lose one of the hydrogen bonding interactions that was giving us a chiral stationary phase, chiral separation previously. So it becomes very, very complicated to predict these separations. And again, that's why we are oftentimes recommending a screening to get started. Nevertheless, let's jump into separations post 2018, and the focus at that point was on achiral cannabinoid separations. Now, when I say achiral, I am saying anything else that's not chiral. So if it's not a pair of left-handed, right-handed compounds, if it's structural isomers, if it's regioisomers, diastereomers, that all kind of gets on this general achiral term for separate. So initially, the focus was on the quantification of delta-9 THC. So based on the Farm Bill, legalization of the regulated production of hemp, by extension, that meant that the production of CBD was also now sort of legalized, but it required that any hemp extract or CBD products that were being produced had to contain less than 0.3% by weight of delta-9 THC, tetrahydrocannabinol. And so those compounds structure shown here. There is no relationship in terms of, again, enantiomers here. They are not related structures in terms of being regioisomers or anything like that. So we would just really call the separation of these two things from each other an achiral separation. So what was kind of the first go-to in trying to establish methods to quantify or ensure that the compounds or mixtures or samples or products that going out contained less than 0.3% by weight THC? Well, the industry naturally adopted methods that were easy, available, and cost-effective. And so most of what was established at that point were achiral reverse phase separations on an ODS octadecyl silane type or C18 type achiral column, and other commonly available achiral phases. Maybe it was phenyl or C8 or something similar to that. Of course, there's numerous application notes and papers and posters and reviews that are available on the topic. And those methods oftentimes are pretty sufficient for establishing, let's say, potency or establishing the quantification of THC in whatever the sample is that's being analyzed. We have, of course, available to us these chiral stationary phases, and so we started to explore what's the possibility of using those phases for the same sorts of analyses. One of the first samples or one of the first separations that we did focused on sort of the greenification or solvent reduction in terms of the analysis of these compounds. So supercritical fluid chromatography is a great way to do that. Supercritical fluid chromatography, unlike HPLC, high performance, or reverse phase chromatography, does not use 100% organic solvent for the analysis. In fact, most of the mobile phase is composed of supercritical CO2. CO2 can be captured after the separation. Of course, we have an abundant supply of CO2, so it's quite easy to get and recycle it. There's a number of advantages beyond that as well. If we just 10 cannabinoids, and I have them all abbreviated here, kind of cut down on the word that can be sometimes. We see if we use tris 3,5 dimethanyl carbamate chiral stationary phase with methanol at approximately 15% by volume with this supercritical CO2, we have a very nice baseline separation, 10 of these cannabinoids, in a very short overall analysis time as well. The pair to kind of pay attention to at the time was peak number 2, which was CBD, and peak number 7, which was D9, delta 9 THC. This gives quite a very nice separation of those two peaks, and obviously then good quantification of THC, which was the kind of important at that moment. If someone doesn't have SFC equipment, supercritical fluid chromatography equipment, because it is a little bit more infrastructure heavy to install a normal phase or HPLC that was already set up, we can do the same sorts of separations of that mixture using normal phase HPLC as well. Here we have that same chiral stationary phase that we used in SFC mode, immobilized cellulose tris 3,5 dimethyl phenyl carbamate. In the normal phase, mobile phase, using 96% hexane, 3% isopropanol, 1% ethanol, and then 0.1% by volume of trifluoroacetic acid. Why did we not use trifluoroacetic acid on the last separation in SFC mode? Because SFC mobile phases contain a small quantity of carbonic acid. And so when we talk about needing to suppress the ionization of acidic cannabinoids in particular, we don't need additives in SFC mode. But when we switch over to normal phase mode, where we don't have the benefit of the carbonic acid, we have to add an extra acid. It could be TFA, it could be formic acid, it could be acetic acid, but something to keep our acidic cannabinoids neutral as they're passing through the column. And so we run that same mixture here. We see we get pretty good discrimination of all of these cannabinoids. And again, we have kind of our critical pair of CBD and delta 9 THC that are very well resolved. So good quantification, good potency analysis in this case. And then, of course, if we want to look at some of the other phases, we don't just have to look at that cellulosic one. We have in the amylose tris-S alpha methyl benzyl carbamate, which is structurally very different from that other chiral selector. And then this is also amylose. With a very similar mobile phase, hexane, isopropanol, ethanol, TFA, we see, again, nice separations across the board and good discrimination of our D9 and CBD, which was, again, still the priority of these analyses. And then going to a more traditional sort of reverse phase separation here, we go back to, or we stay with an amylosic phase. We go with tris 3-chloro-5-methylphenylcarbamate. With a reverse phase mobile phase, it's 45% by volume water, 55% by volume acetonitrile, and then again, TFA as an additive. We get nice separations of all of those cannabinoids that are in this mixture. So early on, really that was what our focus was just to try to find some orthogonality or comparable methods to C18 on these phytocannabinoid mixtures that were being prioritized at the time. Now, the natural progression for us, of course, is that we make these chiral stationary phases. So let's look at some chiral cannabinoid separations then as well. Going back to that reverse phase separation that I just showed you, yes, we separate all of these achiral mixtures, but you'll also notice that CBC, cannabichromene, has 2 retention times associated with it. And why is that? Well, CBC exists naturally in the plant as a racemic mixture. It is both the plus and minus aligned in most of these samples. So we're already starting to see, even when the focus was on achiral, we're starting to see by using these chiral phases, separations of these chiral cannabinoids. So if we zoom in and look at this cannabichromene separation, cannabichromene naturally occurs within the compound, but exposure to UV light will force this cyclic rearrangement and form cannabicyclol. And so kind of one of the ways to fingerprint storage and age of a sample is the amount of CBL or cannabicyclol that's in the sample. So one of the things we looked at was separation of CBC by itself, but then also in mixture with the CBL. And so we have some nice separations here under normal phase conditions, jumping back to this cellulose tris 3,5-dimethylphenylcarbamate using 97% hexane and 3% ethanol. Now, because these are not acidic cannabinoids, we don't need an additive. So this is a neutral mobile phase, which is nice. When we look at things like THC, of course, delta 9 is not just one isomer. It is both plus minus potentially, not naturally occurring, but it can be created or synthetically created as plus minus. Delta 8 is also plus minus. So we can do separations of all 4 of those peaks, all 4 of those compounds under normal phase conditions with amylose tris 3-chloro-4-methylphenylcarbamate and 95% hexane and 5% isopropanol. Here we've got an overlay of the elution order so that you can see where everything is coming out. And if somebody wanted to do the separation in reverse phase mode and let's say make it a mass spec compatible method, we can do the same separation with a different chiral stationary phase, amylose tris 3,5-dimethylphenylcarbamate with 35% water and 65% acetonitrile. Again, here, seeing the elution order, we notice that we have some reversals of elution order or changes of elution order. That's something that we see quite often with chiral separations or using these chiral stationary phases, is that elution orders will kind of move around depending upon the mobile phase and the chiral stationary phase that we're using. So that's a nice advantage that we can have if we need to kind of move things around to get some better limits of quantification. Beyond D8 and D9, we have things like D6 and D10 THC, and so we can separate those on our chiral stationary phases as well. This is, again, cellulose tris 3,5-dimethylphenylcarbamate with 90-10 hexane isopropanol, showing here the elution order. A little bit of a change up in the elution order when we go to amylose tris 3-chloro-5-methylphenylcarbamate. We have some reversals of elution order here using, again, though, hexane isopropanol or even hexane ethanol mobile phases. These are all normal phase separations. CBD, again, not naturally occurring as a racemic pair, but synthetically we can make plus and minus CBD. So we can separate both of those isomers on this amylose tris 3-chloro-5-methylphenylcarbamate in both normal phase mode. That's what you're seeing on the left-hand side of the screen here, hexane ethanol 90-10. But we can also do it in reverse phase mode on the right-hand side. It's the same chiral stationary phase, which is nice. But on the right-hand side here, we've got water acetonitrile 3070. This happened to be a sub-2 micron column, which is, we don't have time to go into why that's important. But with the smaller particle size, we can do really, really fast separations. So you'll notice the time scale here. We're actually doing these chiral separations in less than 20 seconds, which is really, really interesting if you've got a need for high throughput analysis or screening. This obviously would allow you to do some pretty fast throughput. Going back to CBL and CBC, I showed the separation on the left previously. On the right, one of the advantages that we have to using some of these immobilized phases over coated phases, and again, I didn't talk about that because we don't have the time, but the immobilized technology allows us to use some more exotic organic solvents like ethyl acetate and dichloromethane. So revisiting the separation on the right-hand side here, it's the same chiral stationary phase, tris 3,5-dimethylphenylcarbamate, but instead of hexane ethanol like I had showed previously, going to hexane ethyl acetate 90-10 changes the separation quite dramatically. We now all of a sudden see a really, really large separation for CBL, and still maintain a very nice separation of CBC. So we have a lot of handles that we can play with when it comes to chiral separations, solvent being one of those. And then more recently, we were doing some of these acidic cannabinoid derivatives. I showed you CBL and CBC, but those also have acidic derivatives as well, CBLA and CBCA. Here, going with again, we call it an extended range mobile phase. It's like a normal phase, but it's using DCM instead of ethanol or isopropanol or something like that. On immobilized cellulose tris 3-chloro-5-methylphenylcarbamate, we have some nice separations of those acidic cannabinoids as well. This is very much a crash course in chiral separations and chiral chromatography and why it can be important for the cannabinoids. As we're running out of time here, I will share with you my contact information. I would highly encourage this that's interesting to you, or cannabinoid analyses, that you please reach out, and I'd love to have a discussion with you about the work that I've shown you here and maybe how it can apply and help your work as well. Again, my name is Dr. Weston Umstead. I'm the Senior Product Manager for Chiral Technologies. I appreciate your time today in listening to this presentation about our chiral stationary phases and how they can help with the separation of cannabinoid mixtures, both achirally and chirally. And I look forward to having more discussions with you